Okay, thank you very much. Oh, great. Yeah. First of all, I would like to thank the organizers for organizing this wonderful workshop, 3-day workshop, and thank you for inviting me to give a talk. Actually, Alan saved me lots of time. I don't need so much introduction. So I'll be talking about the quantum spin Hall effects in Morie semiconductors. Okay. So TMDs, one thing I just want to highlight is actually that the electrons or the holes are actually located at the K or the K prime point of the Brillouin zone, the two valleys as mentioned by Alan. And also because of the heavy transition metal atoms, there is a large spin-orbit splitting. The spin-orbit field is actually pointing in the outer plane direction because of the mirror symmetry in each of these a monolayer. And so the system actually supports Ising-like spins because the spin can only be up and down, and it has a good SZ conservation in the system. Okay, so that's the only thing that I want you to remember, that actually the electrons, the SZ is a good quantum number at the K and the K prime point of the Brillouin zone. Okay, and then you can twist it to make it a Moiré period like tungsten selenide on tungsten selenide. And as Alan explained, that you actually do a very good approximation. You can forget about the underlying the angstrom scale atomic structure, and just treat the electron with a certain band mass moving in a smooth periodic potential. And as a result, you will get the bands from this big Brillouin zone and zone folded to the mini Brillouin zone and produce a series of flat bands. Okay. And then also, as Alan mentioned, that there are topological bands in the twisted bilayer TMDs. This is actually, you can think of it that before turning on the interlayer hopping, there is the flat bands for the TMD layer number 1 and also the flat bands for the TMD layer number 2. Okay. And Alan mentioned that the holes would like to sit in the A site of the honeycomb Moiré, and then from one of the layers, and from the other layer would actually sit on the B sides of the honeycomb Moiré lattice. And because the electron or the holes, actually I mentioned that they are from the K or K prime valley. Actually, if you look back here, the holes here, they actually behave like they break time reversal symmetry, because there is only one spin down here and one spin up here. But of course, the two valleys are actually related by time reversal operation. And so because the holes actually behave like in each valley, they break time reversal symmetry, the hopping within one layer is actually like an imaginary number. And if you take into account the interlayer hopping, this entire thing just looks like actually the Haldane model in one valley, and the other valley would actually be a time reversal copy. So that actually is really like a K-Malay model in certain limit of the twist angle. Okay. So then you get actually a series of topological flat bands in the system. And this is the earlier continuum model calculation. Alan did not show, so I show here. And at a small twist angle, so this is the work from Alan's group, and this is the work from Liang Fu's group. And indeed, you can actually see that a small twist angle below about 1.5 degree. I just want you to focus on these two bands here. They label that the Chern number is -1 and +1 in one valley, and that's exactly for the Haldane model in one of the valleys here. But on the other hand, when you actually increase the twist angle to be above about 1.5 twist angle, you can actually see that the Chern numbers of the bands actually is now changed from -1, -1, +2. So you can actually build a time binding model for the first two flat bands here, but you can only do it for the first three flat bands here. And there's no name for this model. You can come up with a name for this time binding model. And so this is also very similar results, but the prediction is actually that at a certain angle, you actually get very flat bands. This is from Liang Fu's group, showing that it's really almost like a Landau level in certain twist angles. Okay. And then that's actually the earlier calculation that did not take into account structural relaxations. It seems that recently people point out that it's pretty important, the structural relaxation on the Moiré length scale, and that will actually modify not only the detailed dispersion of the bands, but also the Chern numbers of the bands as well. And this is work from Xiaodi's group showing that you actually get a series of flat bands that have the same Chern numbers for the first three flat bands. And this is from Yang Zhang's group that also showed that actually in this case, all the first 5 flat bands, they all carry Chern number of the equal sign +1 +1 all the way down to the first 5 flat bands. Okay, So because of structural relaxation, the Chern number can change, but I think the main idea is still that to a pretty good approximation, you get multiple Landau level-like flat bands. In this system, they carry the same Chern number. Okay. So this is my very simple schematic for twisted bilayer TMDs with very small twist angle, and you get in a K valley flat bands, a series of flat bands like Landau levels carrying the same Chern number plus 1. On the other valley, K prime, you get a more like the time reversal copy, and you get the Chern numbers of -1 on the other copy. And as a result, if you just feel the Landau level, just feel the first flat band here, put the Fermi level here, then you actually you expect to get a quantum spin Hall effect. The bulk is insulating, but the edge state you get a helical edge state with the spin down propagating in this clockwise direction and the spin ups going in a counterclockwise direction. Okay, so that's for the Fermi level sitting in here. And if you move down the Fermi level, now you actually feel 2 of the flat bands in each valley here, and you actually you expect to get two pairs of helical edge state instead of 1 pair here, and we call it the double quantum spin Hall effect. And it turns out that this is perfectly allowed in this system, because instead the state is actually not protected by time reversal symmetry, but it's actually protected by the spin SZ conservation. Remember that the spin SZ is a good quantum number. So it's perfectly fine to have an even number of helical edge state in the system. Okay. All right, so this is the outline of my talk. I will be talking about the integer and also the fractional quantum spin Hall effects in a small twist angle, twisted Morie telluride and tungsten selenide. And then the second half of my talk, I will be talking about time reversal symmetry breaking actually in a generic feelings of multiple flat bands in this system. Okay, the system I will be focusing on is twisted Morie telluride. It turns out that this is actually quite a magical material. Last year, people have found, including us, the fractional Chern insulators. And but this talk I will be, and also the discovery of the fractional quantum anomalous Hall effect, as Alan mentioned, and I will be focusing on talking about the quantum spin Hall effect published in this work here. So a comment on how to make these contacts. This is the twisted Morie telluride encapsulated between boron nitride. To make good electrical contacts, we actually use platinum electrodes to contact to the Morie telluride. And on top of the entire structure, we also have the top gate and the bottom gate made of graphite electrodes. But on top of the entire structure, we also pattern this a so-called contact gate, CG here, to actually heavily dope the region of the twisted Morie telluride just next to the platinum electrode, so that it can reduce the contact resistance at this junction here. And then the channel here has variable density, and the electric field is just controlled by the top gate and the bottom gate. Okay, and we also put on the split gates to turn off some of the unwanted regions. And one thing I want to mention is actually that once we make this region to be heavily hole doped, the contact resistance is pretty small, and then the contact from this heavily hole doped region to the channel actually is very transparent with this design. And this contact here is nearly independent of the doping density and the electric field that I'm going to show it to you. And with this approach, we can actually achieve a contact, per contact, the resistance is about 25 kilo ohm down to millikelvin temperature. This is not a great number for graphene, which is about an order of magnitude higher than graphene, but for TMD, this is already very good. Okay. The twist angle is calibrated by the Landau fan at a high magnetic field, so we are very confident in the calibration of the twist angle. So I'll be talking about the quantum spin Hall effect in a particular twist angle, 2.1 degree twisted Morie telluride, and I will supplement some of the discussions with a tungsten selenide as well. So I will show you 3 experimental evidence that we actually have seen the quantum spin Hall effect. First is the quantized resistance and the zero Hall resistance. And the second is actually that it's a quantized non-local measurement that really showed that these states are actually really helical edge states, but not chiral edge states. And then finally, I will just show you how what the symmetry is actually protecting this state. It turns out that it's a spin SZ conservation, not the time reversal symmetry. And as I mentioned, it's SZ conserved so that you can actually have multiple helical edge state pairs in the system. And this is a device structure. We have a four contact. It's a 4-terminal device, 1, 2, 3, 4 here, and this region here has a uniform Moiré, and the outside region are disconnected from this region in this device structure. So we have 4 terminal measurements. Okay, so with the improvement of the context, now we can actually do 2 terminal measurements in the system. So what we do here, remember, it's a 4 contact device, 1, 2, 3, 4, schematically shown here. And we short these 2 contacts, we short these 2 contacts and flow a current and measure the 2 terminal resistance. Okay, and that's actually the blue curve here. And you actually can see, and on the right hand side, I'm just plotting 1 over the 2 terminal resistance. So it's actually the 2 terminal conductance like this. Okay, and the red curve is actually the Hall resistance of the sample. Okay, measured under very small magnetic field, like a 0.1 Tesla. This is the Hall resistance. And you can actually see in this case that there are steps of a conductance quantum at, for instance, E square over H, 2E square over H, a weak step at 3E square over H, 4E square over H, so on and so forth. And the different curves here are different electric fields. And you can actually see that the generic states in between the integer fillings, they are dependent on the electric field, but exactly at the integer filling, they are not dependent on the electric field. Okay, so the steps are really clear at this integer filling, especially 1 and 2. Okay, and I just want you now to focus on 3 of the states here, 2, 4, 6, which also has a 0 Hall response, 2, 4, and 6 here. Okay. And so, as I mentioned, the system actually you expect it to have a Landau level like flat churn bands in each of the valley, plus 1 churn number, minus 1 churn number on the other valley. So filling factor 2, you expect it to be a quantum spin Hall effect, and that would actually give you a 2-terminal resistance of 2E squared over H and a 0 Hall resistance, and that's consistent with our experimental observation. And then you move the Fermi level to filling factor equal to 4, you fill 2 of the flat bands, and then you would expect to get 2 helical pairs of H state, and that would give you a 4E squared over H, a 2-terminal conductance with 0 Hall response also. We call it a double quantum spin Hall effect because we have 2 pairs of helical H state. And for filling 6 is a triple quantum spin Hall effect because you have the 3 pairs of helical H state. So these are actually consistent with expectations from the recent band structure calculation. Okay. Okay, another thing that we would like to show is actually, if you're not convinced, that we would like to show that the non-local 2-terminal measurement will also give you consistent results. So this is the idea here. If you have a pair of helical H state, you know, one going this direction, one going that direction, locked to the spin, between 2 electrodes are represented by this, you know, go-like electrodes schematically. Then when you measure the 2-terminal resistance, as I show here, that you will actually get H over E squared with just 1 pair of helical H state. We get H over 2E squared because there's another pair somewhere on the sample, right? But for 1 pair is H over E squared. So the interesting thing for helical H state is actually that if you insert another electrode in between, you know, these 2 electrodes you insert here, the helical H state has to actually equilibrate its chemical potential with this electrode. And so the H state have to come out from the chemical potential of this electrode here. So basically what this electrode does is to cut these helical H states into 2, and effectively it's like a resistor in series, and each resistor carries a resistance quantum. Okay, so it's a pretty weird result in some sense. You insert a gold electrode, you make it less conducting. So it's a bit weird, you know, but this is the nature of the helical H state. You actually make it twice more resistive. Then using our 4-terminal device, we can actually do this kind of measurement. This is the geometry that I have shown it to you. We shot these 2 electrodes, and then you actually can see that there is 1 edge here at the top and 1 edge here at the bottom. So you get 2 edge resistors in parallel circuit like this. Okay, and then next thing we can do is actually to float one of the electrode, and floating this electrode here, not connecting to anything, is almost like, you know, I just insert an electrode in the previous slide here. Okay, then I cut this edge state into 2, so I have 2 resistors in series. And then I have 1 resistor here on this edge. So this is the entire circuit. And then another thing that you can do also, you can do some other variation. Using this 4-terminal device, you can do a lot of variations. You can flow these 2 electrodes, then you cut this edge state into 3. So there are 3 resistors, and then there's 1 here remaining. So form a parallel circuit. And then this is the last configuration. You flow these 2, and then you cut each of the edge into 2, so you get something like this. Then you can work out, you know, using the Landau-Boudica formalism, you can actually work out what the expected resistance are. So that these are the dashed lines for nu equal to 2 quantum spin Hall insulator. The lines of the same color as this configuration are the expected two-terminal resistance you measure in this non-local geometry by floating different electrodes. This is, for instance, this is for this configuration, this value is for this configuration, this is for this configuration, right? And then the solid line are the experimentally measured value, and so this is consistent with actually 1 conductance quantum per edge, and it's a quantum spin Hall insulator. And you can do the same for the nu equal to 4. The data is less nice because of the smaller gap of the double quantum spin Hall insulator, but it also follows pretty good agreement with the expected value according to the dashed line. But the important difference here is actually that you get 2 conductance quantum per edge. It's a double quantum spin Hall insulator. Okay, so I hope that I convinced you that there are actually helical edge states for this quantum spin Hall insulator. Then the next thing I want to address is actually what kind of symmetry is really protecting this edge state. It turns out that it's really not a time reversal symmetry. For instance, you can apply an outer plane magnetic field to the material, and because it's SZ conserved, you apply an outer plane magnetic field, you do not break the SZ conservation. So the SZ conservation still remains, and indeed this conductance step at h over 2e squared, h over 4e squared, they are nearly independent of the outer plane magnetic field up to 1 Tesla, and I'm going to show you later on that it's almost independent up to about 5 Tesla of magnetic field. So breaking time reversal symmetry is really not a problem of SZ conserve this system as long as you apply the magnetic field in the Z direction. On the other hand, if you actually apply a magnetic field in the wrong direction, then it's a problem. If you apply the in-plane magnetic field if for SZ conserved system, then it's actually you are breaking the SZ conservation. You can actually, because of the in-plane magnetic field, you can mix the 2 spins, spin up and spin down SZ field. And in that case, even for a very small magnetic field, 0.1, 0.2 Tesla, you can actually see that there is a suppression of the 2 terminal edge conductance in the state for both the nu equal to 2 and nu equal to 4 states. So in-plane magnetic field, the edge states are sensitive to it. Outer plane magnetic field, the edge states are not sensitive to it. And then you can also do another control experiment. If I turn the system to just conductance to be all controlled, all dominated by bulk states, then you can apply an in-plane magnetic field, and it's just independent of the in-plane magnetic field. As you would expect, if I don't have the edge state, the bulk electrons or the holes are actually Ising-like spins, locked by 1,000 Tesla of spin orbit magnetic field, and apply 1 Tesla in-plane magnetic field, that would not really perturb the system. So for bulk states, it's insensitive to an in-plane magnetic field. Okay, so very similar observation, briefly mentioned, can also be seen in twisted tungsten selenide. This is at a twist angle about 2.7 degree. You can see the step at h over 2e squared for the nu equal to 2 state, and h over 4e squared for the nu equal to 4 states. And these are the single and double quantum spin Hall insulators. And you can also verify that they are exactly at these 2 states. They are nearly independent of the outer plane magnetic field. Instead, the compressible region in between these 2 states, they are dependent on the outer plane magnetic field. But for the in-plane magnetic field, exactly at the 2 and the 4, they are very sensitive to an in-plane magnetic field. But in between, the compressible states are actually independent of the in-plane magnetic field, and that's totally expected for a spin SZ conserved system. Okay, so now I hope that I convinced you at 2, 4, 6 filling the first, second, and third trend band, you produce quantum spin Hall insulators. And then I just want to go back now to the filling 1 state here, and you can actually see that there is a quantized 2-terminal resistance, but at the same time you also get a quantized Hall conductance, Hall resistance. And what's happening is actually that a filling factor equal to 1 without any interaction effect, you only half fill of the first flat band. So the Fermi level is actually cutting through the middle of the first flat band here. And that's without interaction, but actually with interactions, as Alan mentioned, it would favor condensation in the momentum space, and then you actually would favor the electrons to only populate, one of the bands here, and then you actually would just get a chiral edge state instead of a helical edge state, and then you get a quantized Hall effect, and this is known as a trend insulator. And you can also see a fractional trend insulator in this case at the, between filling 1 and 2, but I will skip this part. For filling factor 3, actually this has a 0 Hall response, but a quantized 2-terminal conductance at 3e squared over h, and that would actually mean that you have a 3/2 conductance quantum per edge. And this can also be tested by the same non-local measurement that I told you before. The dashed lines are these for these 4 configurations. The solid lines are the experimental measurement. And indeed, it shows that it's a 3½ conductance quantum per edge. So it shows strong evidence that there's a fractional quantum spin-Hall insulator. And you can also do all those tracks of outer plane magnetic field, in plane magnetic field. Is really just a SZ conserved system. Okay, so lots of theories talking about the fractional quantum spin-Hall effect. But the 2 things I want to mention is actually that some theories predict it's time reversal invariant. Some theories suggest that it's actually time reversal symmetry breaking. And so I'm going to hopefully use the last 3 minutes or something to address this question, that I will show you some results that there is actually evidence of time reversal symmetry breaking for the nuclear 3 states. And this is the work by Kai-Fei Kang, a postdoc in our group. And so this is a map of magnetic field filling factor here and the Hall resistance of the device. Okay, and below filling, between filling 0 and 2, this is the first flat band, first term band. 2 to 4 is the second term band. 4 to 6 is filling the third term band. And first of all, I will actually like to highlight that for the filling equal to 3 states, you can actually see the 0 Hall response persists all the way to 5 Tesla. So it's really, it's not a Chern insulator. It just really persists to a high magnetic field for outer plane magnetic field because of SZ conservation. And then you can also zoom into this region here. Look at here. There's something sort of weird, that there is a jump of the Hall response at 0 magnetic field for almost all the 3 flat bands in any generic fillings. And this is the plot selecting a few line cuts here. You can actually see a jump in the Hall response for almost any filling that you cut, except at filling 2, 3, and 4. Okay. All right. So then we do a more careful scans with the magnetic field. And so let me just go through this slide semi-slowly with you. This is a filling factor equal to 1, so it's filling the first flat term band. It's a quantum anomalous Hall insulator with very well quantized Hall resistance and vanishing RXX. And then this middle 5 panels here is actually filling the second term band in the system. And you can see in any generic filling, this is 2.65, 2.98, 3.02, 3.35. They all have hysteresis behavior in the Hall responses. So it's certainly breaking time reversal symmetry in the system. All the states are ferromagnetic in any generic filling. And you go to the filling the third term band, this is a 5.3 filling. It's already filling the third term band. It's still ferromagnetic, any generic filling. Okay. And then one thing I want to highlight is actually that we are quite puzzled by this observation, is that at filling factor equal to 3, the fractional quantum spin-Hall effect, near the 0 magnetic field, very small magnetic field, there is actually a hysteresis in the Hall response. But then at higher magnetic field, you just go to a 0 Hall response. So basically, it's almost like a filling 3 is a cancelled Hall response, because at lower than filling 3, you have a negative Hall response at positive magnetic field. At higher than filling 3, you have a positive Hall response at positive magnetic field. But somehow at filling factor 3, you just get a 0 Hall response at the positive magnetic field, except very close to 0 magnetic field. Then you get a hysteresis behavior. Okay. And then you can do temperature dependence to try to map out the transition temperature for all the different states. This is filling the first term band. These 2 are filling the second term band. This is the third term band. And you can actually see that this is a measure of the hysteresis. You can actually see that the magnetic transition temperature is always between 2 to 3 Kelvin for any generic filling for the first 3 flat term bands in the system. Okay, so now I summarize. So this is basically like a schematic band structure of the system, and this is the band phase diagram we mapped out so far. Between 0 and 1, we cannot measure, unfortunately, because of the small twist angle and the electrical contacts. And then at generic fillings between the first term band, second term band, and third term band, they are all ferromagnetic except at some of the integer fillings. And then filling factor 1 is a Chern insulator. Filling factor 4/3, I did not have the time to talk about. It's a fractional Chern insulator. And then we get the single quantum spin-Hall, double quantum spin-Hall, triple quantum spin-Hall, depending on the Fermi levels in the system. And then a fractional quantum spin-Hall at filling factor equal to 3. Maybe it's time reversal symmetry breaking, and Liang Fu said that it is totally possible. So yeah, don't ask me and ask him. And so I want to point out that, okay, I'll skip this. And then lastly, I just want to acknowledge the people. who's doing the work. Professor Ji Shan, we share a lab at Cornell. Really, most of the works are done, led by a postdoc in our group, Kai-Fei Kang, and also supported by a former graduate student, Bo Wen-shen, and a former undergraduate student now in Harvard, Yi-Chen Chiu, and boron nitride crystals from the famous Japanese group, and this is funding sources. Thank you for your attention.
Great. We have time for a couple of questions.
So you presented experimental evidence that SZ is quantized.
Yeah.
Why should SZ be quantized?
SZ conserved, right?
SZ conserved.
Yeah,
Why
yeah.
should SZ be a good quantum number?
Because we think that because the holes I think you are talking about, so in monolayer, that you are okay with that, right? SZ conserved in a monolayer TMD for the holes.
In the bulk at the Brouin zone corner, right?
Yes. Yeah. And are you talking about in twisted bilayer? There's no guarantee that it's SZ conserved.
Or at the edge.
Oh, at the edge.
Because momentum is not conserved.
Oh, yeah.
There is strong spin
so
orbit
actually,
coupling.
one thing I want to mention is that, so you have no problem with that, the bulk, the K and the K prime has spin SZ conserved. So you worry about the edge, right? Yeah. One thing I did not mention about these devices is that the edges are actually very smooth. Okay. They are gay defined rather than, etching. Okay. Yeah. So I think that you can accept that, right? Okay. Yeah.
Other questions?
Thank you for the nice talk. I'm just curious, when you're showing the quantized resistance, like why we don't see any more plateau at filling factor 5?
Oh, yeah, we don't really see it. Actually, we can, I did not really show the results. You can also measure, yeah, so let me put it this way. We can also measure compressibility. Filling factor 3 is a weakly compressible state. Up to filling factor 5 is already compressible. We do not get maybe, because we are filling more of the electrons, you get more screening. And filling factor 5, in order to get an incompressible state, you actually need to rely on the interactions. And I think, when you fill many electrons, because of screening, you don't get enough interactions to stabilize the filling factor 5 state. Yeah.
Thank you.
So some of the data, like in particular the data you have here on the left, the two-terminal conductance looks far better than the data that I know best, which was the old data on mercury telluride in terms of the level of quantization.
Yeah, filling factor 2 especially, yeah.
Yeah, and so I wonder if you have any kind of comments on that. Some of the other data looked less quantized, and I just wonder if you have any thoughts on the systematics.
Quantization is always a problem for quantum spin Hall effect, as you know. Because
but here it's quite good, so
yeah, so here I can say why this is quite good in general for the TMDs. We observe many devices probably between, I would say some of the good ones like this one is 2% quantization. The less good ones still below 10% roughly. And the important thing we think is actually the SZ conservation. This really helps. So you can sort of think that, if I have just time reversal symmetry, I apply any magnetic field, I already break the states. But for SZ, I have to apply magnetic field, in some specific direction to get it killed. And second thing I want to mention, these are actually related to Alan's question. This is not edge, this is not the edge-etched device with atomically sharp edge. This is actually an edge defined by the gates. And we use the split gates to turn off those regions that we don't want. So the edge is actually very smooth with the thickness of the BN of the boron nitride, which is probably the edge smoothness is 10 to 20 nanometer. Yeah, something like this.
So the FCI at 4/3, which twist angle was that? Or
it's actually for the Morie telluride in all this entire talk is 2.1 degree.
Okay.
So the 4/3 is also 2.1 degree. Yeah.
And the related question: do you know? Can you say anything about with Morie telluride or tungsten selenide? Does the phase diagrams change qualitatively with twist angle?
Oh, for Morie telluride, but all of these actually are very sensitive to this angle. This is sort of the last slide that I did not really have the time to talk about. For 2.1 degree, you really get a zero Hall response at filling factor 3, for instance. But for, once you go to a 2.7 degree, you actually get a positive anomalous Hall response. And that actually was, also pointed out by a paper from Ting-Xin Li's group and also from Xiaodong's group, saying that this is actually some kind of a, what's the name? Incipient churn insulators, they think. And then if you go to filling factor 3.5, you also get a large Hall response at filling 3, but it's of opposite sign here. So all the physics are actually, for the second churn band, it's very dependent on the twist angle. Okay. Yeah. And the same for the tungsten selenide, but we never see any, fractional churn insulators, those things in the twisted tungsten selenide. Okay. Yeah.
Thanks,
Okay.